So here is midterm 4, question 4, or old midterm 4, question 4 from Haas, which is the following. Consider the function f of x equal to the following piecewise function. It is the absolute value of x times x minus 3 all over x when x is not equal to 0. And it is negative 3 when x is equal to 0. And the first question, part A, for which points is f of x not continuous? Ooh, that was loud. So, for what values is f of x not continuous? If any. He also writes solutions to this one. But I don't think his solutions, I mean, they're fine, but I feel like they could be a little more explanatory or expository. So here's what's happening. This function, definitely continuous everywhere but 0 for sure. When you pick anything less than 0, the function is just this absolute value of x times x minus 3 over x, which is only undefined at 0. It's perfectly fine everywhere else. Same thing if you pick something larger than 0. So 0 is the only place where we might have an issue. So I want to see if it's continuous at 0. So the question we're really answering is it continuous at x equals 0? And this pen is trash. Okay. So we're going to go through our 3 things for continuity. Thing 1, does it exist at 0? For sure it exists. F of 0 is equal to negative 3. Right? There doesn't get much, there's no easier way to define it, right? They're just like, here it is. At 0, it's negative 3. Can't do anything else about that. So it definitely exists at 0. So the second question is, does the limit exist? And this one, although it seems like it's defined to be just one function on either side of 0, this absolute value is kind of misleading. The absolute value really is a piecewise function. If you really, well, in fact, we will. So yeah, I kind of want to erase all this because I need the room. So yes, f of 0 is negative 3. The second part, does the limit exist? So I'm going to look at the limit from the left and from the right. And here's the important thing to, So whenever you have an absolute value, it can be absolute value of x, it can be absolute value of anything. Here's the stuff you have to know. An absolute value function is always a piecewise function in disguise. The absolute value of some stuff is equal to just that stuff if the stuff is positive. Right? Absolute value of 5 is just 5. On the other hand, if the stuff inside is negative, so if the stuff is less than 0, then the absolute value of that stuff is the negative of that stuff. And then people are like, what do you mean it's the negative of that stuff, James? It's supposed to be positive. Well, it is positive, right? If the stuff is negative, then the negative of the negative becomes a positive. So whenever you see an absolute value of anything, you can always say, oh, well, it's just whatever you got inside if the insides are already positive, and it's the opposite of whatever you have inside if the insides are already negative. And that's it every time for an absolute value. So if I'm going to look at the limit as x approaches 0 from the left, well, I'm definitely using this piecewise function. So it's the limit as x goes to 0 of the absolute value of x times x minus 3 over x. But now, since x is negative, right, we are left of 0 or less than 0, that means the absolute value of x is negative x. So the limit as x goes to 0 from the left, x is negative x times x minus 3 all over x. And then, I think I meant to do the other side first, whatever, it's fine. the x's cancel, right? X divided by x is just 1. So it's the limit as x goes to 0 from the left of negative x minus 3. Now we can plug in 0. Negative 0 minus 3 is negative 3, which is 3. And at this point, you could probably stop and say, well, either the limit exists, so it's 3, right? Because the other side would have to be 3 for the limit to exist. And if the limit exists and is 3, the function is not continuous because f of 0 was negative 3. Or the limit doesn't exist, which also means it's not continuous. So once you get to a point where the function's one thing, and either side of one of the one-sided limits is a different thing, you know you're going to have discontinuity. Personally, I think you should finish this part and see whether it actually is that the limit doesn't exist or that the limit exists and is not equal to the function value. And most professors, although they won't explicitly state it necessarily, they would normally like for you to say how a function is discontinuous if it is discontinuous. It is a good practice to be in. So I'm going to look at the limit as x approaches 0 from the right. And I'll point out that if x is approaching 0 from the right, x is larger than 0, which means the absolute value of x is the absolute value of a positive number, which is just the number. So the absolute value of x that I was going to write, I'm actually just going to write x times x minus 3 over x. The x's cancel, and now you plug in 0 for x, and you get negative 3. So this function is discontinuous at 0 specifically because the limit does not exist. The limit as x approaches 0 from the right of f of x is not equal to the limit as x approaches 0 from the left of f of x. And I will also just say more generally, this is usually pretty true if you have something with an absolute value on either side of a number. On one side, it's usually one thing. On the other side, it's usually the opposite value. And I will just, so I'm not going to do this problem right now, but I'm going to write it for you so that you can work on it maybe another time. You could show in a similar way that f of x equal to, what kind of exciting things do I want to come up with here? Sure. X squared minus 2x minus 3 over the absolute value of x plus 1 when x is not equal to negative 1. And what excitingness. Negative 4 when x is equal to negative 1. You can also show that this is discontinuous or is not continuous at x equal to negative 1. And you have to employ the same sort of trick. Well, not trick, same sort of definition. That the absolute value of x plus 1 is x plus 1 if x plus 1 is positive. And it's equal to the negative of x plus 1 if x plus 1 is negative. So I would encourage you to do that on your own for sake. If we have time, we might have time, we can finish this up. We can do this later today, but that's not a bad problem to work on. If we don't get to it today and you want me to show you how it works, I can always make a little video doing it as well. Yeah. All right, let me see what else people have got. So, okay, yes, some good questions. I'm just going in order of what I have in the chat here. Unless I think something is specifically out of order. I feel like I could use some better pennage here. It's hard. So I try not to throw away pens before they're done, but it's also just lame to write with a pen that's kind of faded. So new pen. It's always good to have a new pen. So here's the question from Caitlin. Sorry, well, no, Caitlin's message was not private, so I'm not calling her out in any way. If you write a private message and I say, I don't mean to call out your private message, I'm just sometimes a spaz. Limit as x goes to 0. Oh, 0. I was not expecting a 0 there. Of 3x squared plus sine of x over x times x plus 5. I'm also going to look at the limit as this one goes to infinity, because I feel like that's the question I would ask. Well, let's look at this first. This is a good question. Yeah, so what? So I guess, Caitlin, whose class are you in?
This is Martin, like the TA for Martin gave us this question for, it was like midterm style questions.
Okay, and let me,
Oh, I'm sorry, wait. No, it is, that's right. That's right.
Are you sure it's not as x goes to infinity?
Yeah, it says 0 here.
Okay. And you guys,
I think it's also on Haas's midterm.
also what?
On Haas's midterm, like
Which
practice. I think it was midterm. I did 1 and 2, so it's on. I don't know which one it is, but it's one of those.
Yeah, let me see. I'm just curious about one small thing here.
Yeah, they have yeah, I'm in Martin too, and it's both limit as x approaching infinity, and then the second question is the same thing, but limit as x approaches 0.
Okay. Because infinity, no sweat. 0, a little bit of sweat. Maybe a lot. Okay. Right. Oh, okay. Whew. Yeah. Okay. 0. So, okay. Now that I've looked at the answer, I know what it is, but not, well, I should say so I looked and I saw that the answer is 1/5. Okay. So I'm trying to think about how I would know what to do here without having known what the answer was before that. So I guess I should do the usual things I would normally do. If we plug in 0, what do we get? We get 0 over 0, right? 0 on top, 0 on the bottom. And now here's what I should have maybe tried to see that I didn't. I kind of see a sine x over x. And we know that as x goes to 0, sine x over x is a limit that is 1. So since I'm seeing that, I think it might make sense to break this up. So I'm not positive though. I'm a little unsure about the stuff I'm about to take right here. But you know what? You have to try something. So I'm going to try writing this as the limit as x goes to 0 of 3x squared over x times x plus 5 plus sine of x over x times x plus 5. That is a perfectly legitimate move. Oh, okay. All right. So this one was still kind of throwing me off, but I think I see what to do. So let me ask you guys, what can I do with this expression? Is there any simplifying I can do?
Can you cross out the x from the denominator with the 3x squared?
This x with this x. Right, 3x squared, I cancel one of the x's, I get 3x. So then I've got 3x over x plus 5. And now I can plug in 0 and get 0 over 5, which is defined, right? It's equal to 0. And then for this one here, so I'm actually going to write the limit of this plus this is the limit of this plus the limit of this. I'm using one of those limit rules. This says the limit of a sum, right? The limit of something added to something else is the sum of the limits. And here's what we want to do with sine x over x times x plus 5. We want to break it up into a piece we like, sine x over x times the rest. Okay. If I break it up into sine x over x, what's the other fraction I still have to deal with?
1 over x plus 5.
Perfect. Great, now we can do it. Because now this part here is going to be 0, right? It's 0 over 0 plus 5, which is 0, plus the limit as x goes to 0 of sine x over x is 1, and the limit of 1 over x plus 5 is 1 over 0 plus 5. So I end up with 0 plus 1 times 1/5, which is 1/5. That's a little bit tricky, I'm not going to lie.
Do we need to put the limit as x approaching to 0 before the sine x over
You
x.
probably don't have to. You can probably totally get away with just writing it like this and still be perfectly fine.
Okay.
Yeah, of course, Caleb. I'm happy I solved it too. It was a kind of a challenging question.
Are we allowed to just multiply by 1 over x and then just plug in 0 from there?
What step are you at?
Like if you start from the beginning, just like looking at the problem. Because what I did, I just multiplied it by 1 over x, because then you would get like just like 3x squared over x plus 5, and then I plugged in 0.
So
You got one.
I guess I'm not. So you're saying you're wanting to break it up like the limit as x goes to 0 of 1 over x times 3x?
Times the whole thing.
Like that? Is that what you're saying?
I would still have the x next to the x plus 5 on the denominator.
So I can't just multiply by 1 over x, because then I'm changing the thing.
Okay.
The only thing we're allowed, what's the only thing we're ever really allowed to multiply by? 1. Right? If you multiply a limit by anything other than 1, you change its value.
Okay.
So yeah, I can't just multiply by 1 over x.
Okay.
But let's also do the other part of this question, which is the limit to infinity, because that actually brings up something that is important, which I have to imagine will show up on your test one way or another. Which is why I thought it was a limit to infinity at first, anyway, because it looked more like a limit to infinity question. Although it's certainly a perfectly valid and I would say it's a hard question, but it is a reasonable question, the one we just did to ask, I think. It is not out of the realm of reason. So 3x squared plus sine of x. And the bottom is x times x plus 5. Yeah, I guess I should write it that way. Okay. Now, if I'm doing a limit to infinity, I really do want to multiply out the top and the bottom just to kind of make sure that I can see what's happening. So even if you don't have to write it necessarily, but it's worth at least thinking about the fact that it's 3x squared plus sine of x over x squared plus 5x. And we're so close to having a rational function, right? If this was 3x squared plus x over x squared plus 5x, you guys could all tell me, you can type in the chat, you can show me your fingers if you have your camera on, which I don't think anyone does, which is fine. You can tell me that this limit, if this was an x instead of a sine x, what would that limit end up being? Of 3x squared over x squared plus 5x as x goes to infinity. Yeah, exactly, right? We would get 3 over 1 because it would be the quotient of the leading coefficients, because this term and this term have the same highest power and they are the dominating terms. Now here's the thing. That's essentially still true. This limit is going to be 3 for that same sort of reason. The problem here is that you can't just say it's 3 because you have a rational function over another rational function. The degrees are the same, because really we don't have a rational function. The thing on top is not a polynomial. There are 2 ways to do this question. I'm going to show you both. And I'm going to show you the way I kind of usually do it first, and then I'll show you the way you'll probably like better. But I think this way makes more sense to do it. So here's the thing you should always, here's the thing you should most of the time think. When you see a limit to infinity and there's a sine or a cosine, you should think about sandwiches or the squeeze theorem. When you see a limit to infinity and sine or cosine, you should think, oh, I'm probably going to have to use the squeeze theorem. It's not 100% true, but it is mostly true. Because here's the thing. I don't know, in fact, none of us know, because it's not knowable, what the limit as x goes to infinity of sine of x is, because it keeps oscillating. It goes back and forth and back and forth and back and forth and back and forth between 1 and -1, right? But it is always between 1 and -1. And it doesn't matter if it's sine of x or sine of something super crazy. It's still always between -1 and 1. So what I always want to start with, when I see a sine or a cosine and something going to infinity, Or it could even be something like this. The limit as x goes to 0 of sine of 1 over x, right? Where the insides are getting infinitely large. So I don't really know what the sine function is doing. I'm going to start by saying, well, I don't know what sine's doing, but I know it's stuck. I know it's stuck between -1, 1. And then I'm going to manipulate my middle, well, actually my whole inequality, but specifically in a way so that the middle part looks like the thing I'm trying to take the limit of. So first I'm going to make this look like the numerator by adding 3x squared to each piece of the inequality. So I'm going to add 3x squared. So I'm going to get 3x squared minus 1 is less than or equal to 3x squared plus sine of x is less than or equal to 3x squared plus 1. Still true, right? If sine of x is less than or equal to 1 and bigger than or equal to -1, I can add the same thing to each piece of the inequality, and the inequality is still true. And then we're going to divide by the denominator, x squared plus 5x. So I'm going to divide each piece by x squared plus 5x. Great. Now we have the middle of our compound inequality looking like the thing we want to take the limit of, and that is key. You have to get that. Well, there's another way to do it where you don't exactly have to get that, but I'll say that in a minute. So now, after you've got the middle looking like you want it to look, you take the limit of the other pieces. So I'm going to take the limit as x goes to infinity of 3x squared minus 1 over x squared plus 5x. Now, I think in a squeeze theorem problem like this, you shouldn't have to show the work of dividing everything by x squared. I think you should just be able to say, oh, look, it's a rational function now for real. The degree on top and the degree on the bottom are both 2. So the limit is the quotient of the leading coefficients, which is 3 over 1. I think you should just be able to say it's 3 without having to show the work. But if your teacher thinks you have to show the work, your teacher thinks you have to show the work. So do whatever you need to do. And then similarly, the limit of this part is x goes to infinity of 3x squared plus 1 over x squared plus 5x. Well, it's still the same situation. It's still a rational function. The degrees are still the same. The leading coefficients are still 3 over 1. All right. So now the limit of this is 3, the limit of this is 3, and this thing that's between them, its limit is also between them. So we can say by the squeeze theorem, which I like to abbreviate with ST, by the squeeze theorem, the limit is x goes to infinity of, I know I'm getting kind of very slanty here, 3x squared plus sine x over x times x plus 5 has to equal 3. And that's how I prefer to do this type of problem. But I will mention there is a different way. But first, are there questions about this?
So was it just a coincidence of that by squeeze theorem is the same answer as if we just took the coefficient?
It is not.
Or is it?
No. It is basically, you could think about it, sine of x in a rational, well, in a semi-rational expression like this, the sine of x really isn't contributing anything. So I'm really kind of thinking, I'm just replacing that with a 1, or really a plus or minus 1. And oh yeah, well, of course, the limit of that is going to be 3 over 1. So no, it is not a coincidence at all. You can totally expect the limit to be what it would normally be. The thing is, it wouldn't be appropriate to just, well, in fact, I'm going to show that in the next step, but it wouldn't be appropriate to just say it's 3 because of the things we know, because you have this squeeze theorem kind of element to it, but you still know what the answer is going to be. Someone else was going to ask something too?
Yeah, I did it differently.
Sure.
Can you?
Yes.
So normally for a rational function, you just divide by the highest. Is that what you're going to show us?
Yeah, exactly. Yes. There, like many math things in life, there are often multiple ways of attacking the same problem. So another way to attack this problem, the limit as x goes to infinity of 3x squared plus sine of x over x squared plus 5x, is to do exactly what you think you should do. Divide everything by the highest power of x in the denominator, which is totally fine. That's the limit as x goes to infinity. I'm just going to show the divided. So 3x squared divided by 5. I'm going to show the word fine. So divide each thing by x squared. And then we get the limit as x goes to infinity of 3 plus sine x over x squared over 1 plus 5 over x. Okay. So now what do we do? We know 5 over x goes where? To 0. What about sine x over x squared? Well, this is where you have to use the squeeze theorem again. So either way, when you do this problem, I think you have to use the squeeze theorem. So here's what I would probably actually do. I would probably actually go to the limit rules here and say, oh, this is equal to the limit as x goes to infinity of 3 plus the limit as x goes to infinity of sine x over x squared over the limit as x goes to infinity of 1. I might not actually do this, but sorry. Limit as x goes to infinity of 5 over x squared. And then I would say, so I know the limit of a constant is the constant. Same deal here. I know the limit is x goes to infinity of 5 over x squared is 0. And I'm pretty sure this is 0, but we don't actually have a rule for this, right? We have a rule for a constant over x to a positive power if x is going to infinity. But for this, we actually have to use the squeeze theorem. So I would say that this is 0, but I would actually show some work up here. Say, oh, this is 0 because, well, sine x is less than or equal to 1, bigger than or equal to negative 1. Divide everything by x squared. So in fact, just divide everything by x squared. And then the limit of this is 0 as x goes to infinity. And the limit of this is 0 as x goes to infinity. And since both those limits are 0, the limit of that is also 0. So by the squeeze theorem, the limit as x goes to infinity of sine x over x squared is 0, which is how we get the 0 there, which is how we get the overall. Either way you want to do it is fine. I feel like the first way looks maybe slightly nicer, but really you should do whatever you think works better for you. Does that answer the question of the person who was asking about doing it the other way?
I actually did it a different way than that.
Okay, what'd you do?
I factored out 1 over x from sine x squared.
Okay.
And since I know the limit of 1 over x as x approaches infinity equals 0, it just canceled out because you multiplied by 0.
That's not always true.
Oh.
The problem is that's true as long as the other limit isn't infinity. And which is true here, but you have to say something about that. So I want to make this, you actually bring up a really, really excellent point. So, and I'm going to show you an example of this. It's going to feel kind of dumb, but it shows it. So what's the limit as x approaches infinity of 5? Well, we know it's 5. But I can't do this. I can't say it's the limit as x approaches infinity of 1 over x times 5x, and then say that that's 0. Because it's not 0.
Yeah, that makes sense.
But really it's because in this particular example, it's a 0 times an infinity. So, and which is an indeterminate form. It is perfectly okay to break up a limit of a product as a product of the limits, as long as each of those factors exist and are real numbers. Infinity is not a real number, so that's why we can't do it here. You could totally do it for the one you're talking about, or you could say, oh, the limit as x goes to infinity. You could say 1 over x times sine x over x. This limit's 0. This limit is also 0 by the squeeze theorem. So you're still kind of stuck using the squeeze theorem. I do think really genuinely, if you have a limit to infinity and you have a sine or a cosine, definitely the intention of your teacher is to make you use the squeeze theorem. So you probably have to use the squeeze theorem. Okay. It's getting warm in here. It's all right. So let's see what else is on the chat agenda here. Oh yeah, okay, cool. So yes, I think we talked about a limit kind of like this last time, where you have a limit to infinity instead of a limit, like a delta epsilon limit to infinity. Well, let's look at this one. So our function is f of x is equal to, what have I got here? 3x plus 7 over x. Yeah, we definitely did one like this last time. That's perfectly fine. So let epsilon be greater than 0. So I should say, we're trying to prove, using the precise definition of a limit, that the limit as x goes to infinity of this function, 3x plus 7 over x, is equal to what? Well, what is the limit? It's, oh, I see that Caitlin already wrote it. It's 3. I'm just kidding, Caitlin. That was your answer to your previous question, but it's still the right answer. So we're trying to prove that. And we're going to do the thing, right? So we're going to let epsilon be greater than 0. Now, here's the thing. Normally, we would write the following thing. We want to show don't write this down if you're writing stuff down, because I'm going to erase this. We want to show there is a delta greater than 0 such that x minus a less than delta implies that f of x minus the limit, which is 3, is less than epsilon. Or in less mathy words, normally if we were doing a regular-ish delta epsilon proof where we weren't going to infinity, we would be trying to say that x is close enough to the thing x is approaching so that f of x is close enough to the limit. And of course it had to be 3. I'm going to get my 3's and epsilon backwards again, right? This says x is close to a, where x is approaching it. This says f of x is close to 3, the limit. How close? Epsilon close. The difference here is that x isn't getting close to any one particular number. X is just getting bigger and bigger and bigger and bigger and bigger. So instead of saying we're going to show that x is delta close to some a, we're going to show that x is big enough so that f of x is close to 3. So show that there is a, usually call it a capital M, such that x being larger than m, right, x is far enough out, implies that f of x minus 3 is small, or that f is getting close to its limit. And then I am never good at these. That doesn't mean we can't do it though. So actually let's go to the other side of the board and do our scratch work. So here's what we're trying to get. We're trying to get f of x minus its limit to be less than epsilon. F of x was what, 3x plus 7 over x, I think. It's in the chat. There it is right there. Minus the limit, which is 3, less than epsilon. We simplify this. We get 3x plus 7 minus 3x over x, so minus 3x over x less than epsilon. 3x is canceled. You get the absolute value of 7 over x less than epsilon, which you could write as 7 over the absolute value of x is less than epsilon, or multiplying by absolute value of x divided by epsilon, 7 over epsilon is less than the absolute value of x. Now, since x needs to be positive anyway, we can drop the absolute values and just say, oh, we need x to be bigger than 7 over epsilon. So that's what we're going to set equal to our capital M. And please,
how do you make the absolute value over x when it's originally like over the 7 over x?
Oh, well, because so if I have like the absolute value of a over b, it's equal to the absolute value of a over the absolute value of b.
Okay.
Right, because what's this really saying? Give me some numbers and give me the positive thing at the end. Well, it doesn't matter if I divide them first and then make it positive, or if I make them both positive and then divide. Either way, it's still going to end up giving me the positive thing. So that's how I broke. And then I said the opposite value of 7 is 7, so I just dropped it.
Can we put on the left side is 0 is less than that to get rid of the absolute?
Maybe. I'm really just thinking about the fact that I know x is going to infinity, so I don't really need to be talking about the absolute value of x since x is already super duper positive anyway. That's kind of my idea. But yeah, maybe I should be saying something about how this is greater than 0. It doesn't hurt. Okay. So then this is where I'm always kind of like, how much do we write? Well, I don't know. So let m equal epsilon over 7. Nope, I'm sure it's 7 over epsilon. Then x greater than m implies, and this is where you can either be like, implies by all the work we did before that the absolute value of 3x plus 7 minus, over x minus 3 is less than epsilon. Or you could show the work. You could say, oh, then, so you could either do this or you could do this. X greater than m means x is greater than 7 over epsilon, which means 7 over x is less than epsilon. You guys see how I got there? Right, okay. And then we can throw some absolute values around that. If something is less than the number, it's absolute. Yeah, this positive. So then this. And then we can make this look like what we want it to look like. This is really the absolute value of 3x plus 7 over x minus 3. So I don't know how much of this you really need to show. I would, if I had to guess though, I would err on doing it this way. But then that's what we wanted, right? We showed that if x is big enough, f of x is close to 3. That's what we wanted to show. Are there questions? It's really okay if you have questions. You're like, I would have questions if I was. Okay. All right. In case you're curious, it's because I was just justifying it to myself in my head, right? We said epsilon was positive. So 7 over epsilon is positive. So x being bigger than 7 over epsilon means that x is positive. And so that 7 over x is the same as the absolute value of 7 over x, since this is already positive. So I was kind of having trouble justifying that to myself in my head, but now I see, oh yeah, it's perfectly fine to just say this and this are the same because this is already positive. So hopefully that wasn't tripping anyone else up like it was tripping me up. I would be fairly surprised if there wasn't some sort of precise definition of a limit question on your test. I would like to imagine it wouldn't be ridiculously hard. I don't actually know.
Hey James, I understand like the formatting and all that, but like conceptually, I don't understand how it works, like why it makes sense.
So again, when you're trying to prove a limit, what you're saying is that if x gets closer and closer to the thing it's supposed to be getting closer to, either a number or infinity, right? Basically, you can find a condition on x so that the function is as close to the limit value as you want it to be, right? Because again, what you're really saying when you say the limit as x goes to infinity of 3x plus 7 over x equals 3, you're not actually saying that this is ever equal to 3. And it's not, although it could be sometimes. What you're saying is this expression gets really, really super freaking close to 3. How close? As close as you want. How close? Epsilon close, right? Because we can make epsilon as small as we want. So here's maybe a better way to kind of explain what I'm saying. I just want to point out that I can make this function as close to 3 as I want. And I'm going to pick some ridiculously small number. I'm going to pick, maybe not that ridiculously small. I'm going to pick 1/1000th. So I can be like, okay, I can make 3x plus 7 over x within 1/1000th of 3. Meaning I can make their difference less than 1/1000th. How do I do that? By making x large enough, right? Because as x gets larger and larger, this fraction gets closer and closer to 3. How big do I make x? Let me check. I make x bigger than 7 over epsilon. So I can do that by making x larger than 7 over that number, which is equal to 7,000. Okay, so let's see. I'm gonna make I'll make it 7,001. So if x is 7,001, then I'm gonna have 3 times 7,001, which is 21,003. 21,003 plus 7 all over x, which is 7,001. And let's see, that's going to be 21. Whoops, 21. Yeah, sure, 21. So that's going to be 21,010 over 7,001. I definitely need a calculator for that. Doing that division, 21,010 divided by 7,001, I get 3.000999857. So look, I picked some arbitrary condition, and I found that x has to be that big so that the function is within that amount of 3, right? This is 3, or I should say this is less than 3 plus 1/1000th, which is 3.001. So again, to kind of sum up, right? And I know it feels kind of weird. You're saying this really proves that the limit is what it is. Yeah, it does. Because again, the limit being 3, all this means is that you can make the function as close to 3 as you want to. And it gets really, really close to 3. It's never equal to 3, but it gets closer and closer and closer and closer and closer forever and ever and ever and ever, right? It's kind of dumb to say it like that, but right, we're just saying I can make this function really, really close to 3. How close? 1/1000th, or 1/1,000,000th, or 1/1,000,000,000th, or 1 over 10 to the billionth power, right? You can make it really, really close to 3. And this proves that. This proves that no matter what you pick as your bound for how close to 3 you want to be, there is always an x that if you go that far out towards infinity, that you can be within that word I'm looking for. You can be within that amount of your limit, right? So we could pick a smaller number here and had to find a corresponding larger number here. And in this particular example, we actually have an exact correspondence, right? We know that for whatever epsilon you pick, x has to be bigger than, 7 over epsilon. So the smaller the epsilon, the larger the x. Does that kind of spell things out?
Yeah, thank you.
You're welcome. It's not always the easiest concept to grasp, that this is actually a proof, right? This is a literal proof. We have actually proved that this limit of this function is actually 3. And again, I'm going to stress one more time just to make it super duper clear for everyone. That doesn't mean that this function is equal to 3 ever. It's not, right? You could actually rewrite this as 3x over x plus 7 over x, which is 3 plus 7 over x. 3 plus 7 over x is never going to equal 3, because 7 over x is never going to equal 0. But it is going to get as close to 3 as you could possibly get without actually being equal to 3. Okay. I think I've said it enough times. Maybe. And that's the idea with any limit, right? Whether you're going to infinity or, right, whether you're proving the limit as x approaches 2 of 5x plus 1 is equal to 11. For that kind of thing, you're saying, oh, I can make x as super close to 2 as I need to, so that the function is as close to 11 as I want it to be. In that case, it would actually end up equaling 11 if x was equal to 2, but the idea is still the same sort of thing. All right, I feel like there's another thing in here. Yes, okay, let's look at this one. We've got this lovely looking, oh, graphing. Who's making you guys graph stuff already? So here's the question that I've been asked. Y equals x cubed plus x squared minus x minus 1 over 2x squared minus 6x plus 4. And we want to find essentially everything. Asymptotes, intercepts, discontinuities. So asymptotes, intercepts, discontinuities. If someone specifies discontinuities in addition to asymptotes, it means they're probably expecting there to be a hole, right? Because most of the time for a rational function, discontinuities look like vertical asymptotes, right? This function is discontinuous when the denominator is 0. Usually that's a vertical asymptote, but sometimes it's extra special and it's a hole instead of a vertical asymptote. I feel like there's something else on the list. Oh, and then to graph the terrible thing. Again, I feel like, well, I should point out, I don't know what the heck Molossi is doing. Like, I really, not that I think he's doing crazy things. I'm not tuned into what is going on in his class. I do know that he's going kind of in a very weird order. And yeah, if you are in Molossi's class and you have questions in general, you should definitely email me. Let me know what you have questions about what's going on, or post a discussion. That's also good. But let me know it's Molossi's class, because I know that he is doing things in a very different way. So when I'm graphing something, or when I'm doing the work to try and graph something, I usually go in the order of first finding intercepts, then finding asymptotes, and then maybe discontinuities. And really, there's kind of two things to be aware of. This is what I think of as the unfactored form of the rational function, right? I haven't factored the top, I haven't factored the bottom. And I like this for finding the y things, meaning I really like the unfactored form for finding the y-intercept and for finding any horizontal asymptotes. To find the y-intercept, what do we always do to find the y-intercept? We set something equal to 0. Is it y or is it x? You guys there? You guys there? You guys there? You guys there? After this problem, we'll take a break. To find the y-intercept, you set x equal to 0. So I set x equal to 0. It's super easy to see. If x is 0, I get 0 plus 0 minus 0 minus 1 over 0 minus 0 plus 4. So if x is 0, y is negative 1 on top, 4 on the bottom. Do I have a horizontal asymptote? The answer is a resounding no. I do not have a horizontal asymptote, because the degree on top is strictly larger than the degree on the bottom. But I'm betting we do have a slant. Well, in fact, I'm not betting. I'm betting the teacher probably wants us to also talk about there being a slant asymptote, because the question just said asymptotes. So this one does have a slant asymptote, because the degree on top is strictly 1 larger than the degree on the bottom. So slant asymptote, we did this last time, we should still do it again. And this one's going to be, fun, yeah. So before I start finding the slant asymptote, I really should do some other work. I'm going to come back to that then. I also do want the factored form, because the factored form is really going to help me find the x things. like the vertical asymptotes and the x-intercepts. So the denominator I can definitely factor out of 2. I'm left with an x squared minus 3x plus 2. And that does factor further. That factors as x minus 2 times x minus 1. Now, the top is a little trickier. And I don't know if you talked about this, but the top does factor. It factors by grouping. I would also just check to see if either one of these 0, so x equal to 1 or x equal to 2 was a 0. And 1 is. When you plug in 1, you get 1 plus 1 minus 1 minus 1, which is 0. So I know that x minus 1 is going to be a factor because x equal to 1 was a 0. But here's how I probably actually factor it. I factor by grouping. From this first 2 terms, I can factor out an x squared. I'm left with an x plus 1. From the second 2 terms, I can factor out a minus 1. I'm left with an x plus 1. And then I can factor out an x plus 1 from each of these. I'm left with an x squared minus 1. Finally, I can factor the x squared minus 1 as x plus 1 times x plus 1 times x minus 1 all over 2 times x minus 2 times x minus 1. And then, now here's where we have to be extra super duper careful. You can cancel these x minus 1s. So that means our function looks like x plus 1 times x plus 1 over 2 times x minus 2. But x is not allowed to equal 1. Because if x was equal to 1, you get 0 over 0, which is undefined. Okay, I feel like someone might have had a question at this point. Okay. So now I want to find the x things. So I want to find the x-intercept. So the way we find the x-intercept is saying y equal to 0. So now it really is better to look at the factored and canceled form. So if I set y equal to 0 here, I'm going to get negative 1 and 1 as an intercept. The negative 1 can't be an intercept because the function's undefined there. So I'm going to set the factored and canceled form x plus 1 squared over 2 times x minus 2 equal to 0. And when you set a rational function or a fraction equal to 0, the only way it's ever equal to 0 is if the top's equal to 0. So x plus 1 squared equal to 0, negative x equal to negative 1. That is my one and only x-intercept. Vertical asymptote we get by setting the denominator equal to 0. 2 times x minus 2 equals 0, x equals 2. So I've got almost everything. This problem is not easy. This is kind of a lot of a problem. We've got the x-intercept of negative 1, the y-intercept of negative 1/4, the vertical asymptote of x equals 2, a hole at x equals 1, and a slant asymptote that we haven't found yet. Slant asymptote is going to be especially terrible here. Now, I will mention, I feel like it's silly to be asking this kind of graphing question at this stage, because really we're going to learn more tools for graphing this kind of thing even better once we've talked more about derivatives and finding the maximum and minimums of a function. But I'm not the teacher of the class, so this is what they're asking, this is what they're asking. So instead of doing polynomial division with this, we're going to do polynomial division with that. So I've got x plus 1 squared over 2 times x minus 2, or x squared plus 2x plus 1 over 2x minus 4. And this is going to kind of hurt. So I've got, maybe there's a better way to do this. I don't know if there is. I'm just going to do the polynomial division. So here's the question that I don't like the answer to. What do you multiply by 2x to get x squared?
0. Oh my god.
You need an x, right? Because x times x is x squared. But then you need a 1/2 so that the coefficient works out correctly. So 1/2 x times 2x is x squared. And 1/2 x times negative 4 is minus 2x. Subtract. X squared minus x squared is 0. 2x minus minus 2x is 2x plus 2x, which is 4x. And then we repeat the process. What do you multiply by 2x to get 4x? Yeah, thank you. And then you can stop, right? Once you get that last part of the quotient, that constant term, you don't have to continue with the process. You don't have to be like, this is 4x minus 8, subtract, and you get 9. Right? That is not necessary at all. All we need is this. So our slant asymptote is y equal to 1/2 x plus 2. All right. Now we're supposed to graph this thing. Okay. Do you guys mind if I erase this work so I can do the graphing on this side? I'll give it a slow count to 5. Now, speaking of which, while I have a second here, I'm going to take a picture of the names. Cool. Enter the roll lever. All right, so there's our slant asymptote. Now we're going to try and graph this hot mess. Also, you know, Desmos is a thing, right? Not that you shouldn't do this work, but you can also check it on Desmos, unless that's against the rules or something. I would be certainly checking my graphs on Desmos if I was graphing things. So let's see what we've got. We've got x equal to -1 as a x-intercept. I've got y equal to, I think it was -1/4 as a y-intercept. I have a vertical asymptote of x equal to +2. And I have a slant asymptote of y equal to 1/2 x plus 2. So for a slant asymptote, you actually want to think about finding the line, right? So that line, y equals 1/2 x plus 2, has a y-intercept of 2, right? X is 0, y is 2. Has an x-intercept of y is 0, x is going to be -4. Those aren't actually points on my graph. Those are points on my asymptote. So -4, so 1, 2, 3, 4, and +2. So I'm going to go through those 2 points right there and right there. Okay. And then finally, actually, I think, then we've got a whole one, which we'll deal with it after we graph the thing. All right, so here is my tried and true method, which might not be so tried or true. Here's something that is good to know if you're graphing in general. You can only cross the x-axis if you have an x-intercept. And sometimes you don't even cross that, sometimes you bounce off. I'm going to start at my y-intercept, which is notably below the x-axis. I'm going to start right there. If I move to the right, where I don't have any x-intercepts, as I move towards this vertical asymptote, when you get close to a vertical asymptote, you either have to go down to -infinity or up to +infinity. Which way do I have to go here? To -infinity or to +infinity?
Negative.
Right. And the reason I can't go to +infinity is because I don't have an x-intercept where I could cross the x-axis there. So I'm stuck. I'm forced to go that way. And I really would like to have my equation back over here. So again, remember we're graphing y equals x plus 1 squared over 2 times x minus 2, and x can't equal 1. Okay, Now, on the other side of this asymptote, we're either going down to negative infinity or up to positive infinity. And you can either, there's a couple ways you can see what's going to happen here. You can say, well, if it went down, then I'd have to go up like that. I'd have to cross the x-axis to be able to eventually get closer and closer to my slant asymptote, which I can't do. You could also actually just plug in the point, right? You could plug in 3. If you plug in 3, the top is positive, the bottom's positive, so the whole thing's positive. So we actually have to be going up to positive infinity this way. And then eventually you have to turn around. Now, once we learn more about derivatives, we're going to be able to find this point, which is a relative minimum of the function, right? Where it's smaller than all the things that are next to it. Over here on the other side, starting at my y-intercept again, I'm going to get closer. I'm going to hit my x-intercept. And then the question is, do I cross or do I bounce off? Well, you can either plug in the value like -3. And see if I plug in -3, the top is positive, the bottom's negative, so overall it's negative. You could also see that this factor, this intercept of -1, came from a factor with an even power, which means that x-intercept has an even multiplicity, which means you bounce off the x-axis. Or you could use Desmos to give yourself an idea of what it looks like. Okay, I'm not done though. You thought I was done, I'm not done. There's a hole at +1. So right here, when x is 1, there's a hole. And typically, I think it is, you should definitely, if there is a hole, you should find the value of that hole. Meaning, if you plug in 1, even though you're not allowed to, you can still plug in 1 to see what it would be. Y would be, let's see. If x is 1, y is going to be 1 plus 1 squared, so 4 over 2 times 1 minus 2, which is -2. So the hole is at the point 1 comma -2, which I actually did a decent job. No, it looks more like I graphed it at 1, -1. Oh, well, that's life. So that's how you graph this one. I will again say, well, actually, no, I won't say. No, I won't say. Right, later on, we're going to have the tools to figure out what's that point. Right now, we don't know. But it is a point that we usually care about graphing. All right, I'm going to say a couple things because I feel like this is worth knowing. But we're going to move very quickly past this. So, might have some function. Might look like this. You might call it f of x. You might call it f of t. The idea is we're trying to find the slope of the tangent line at that point, also known as the rate of change of the function, right? The function is y, the independent variable is x. We're asking how y is changing as x is changing at a particular point. Here is definitely a positive rate of change, right? Y is changing positively as x moves from left to right. Whereas over here, the rate of change would be negative. Right here, y would be changing in a negative direction, right? It would be decreasing as x moves from left to right. We're always in the context of x moving from left to right. But if we look at this point in particular, I'm interested in, oh, well, what's the slope of that tangent line? Or what's the rate of change of the function at that point? And so, of course, the idea is that we need a limit. We need a limit of a different slope. So we're going to take some other point. Here, I suppose I should label my points. Depending on how much pen you want to get on your hand. Sorry, 1 second. Pen on my hand is the worst. Sorry. So, right, the idea here is that this line between these 2 points has some other slope of the secant line. And there are various ways of labeling these points. The way we like the best is to typically call this point x, which I know is kind of weird because you're saying it's f of x, but just that's why some people call this f of t and t, but don't worry about it. And this point here, x plus h. So that this distance between them is h. That means this y value is f of x, which again, I know is a little weird. Don't sweat it. And this y value up here is f of that input, which is x And then, of course, the slope of the secant line is the difference in the y's. So f of x plus h minus f of x over the difference in the x's, which is x plus h minus x, which is just h. And then here's kind of the really salient point. To get this tangent line, you're going to just scooch this point over until it gets closer and closer to the point you're actually trying to find the tangent line at. And what happens when you do that is this secant line, which I'm going to try and draw a bunch of them, it's probably going to make my graph look totally messed up. Right? There's another secant line. There's another secant line. Right? The secant line, so I actually did a not terrible job of that. I think that looks pretty good considering my limited graphing abilities. You can kind of see, actually, this time, that the closer this point gets to that point, the closer the secant line slope becomes to the tangent line slope. And so the whole idea here is that the actual slope we're finding there is the limit as this point moves over there. So you could either say the limit as x plus h approaches x, or you could say, well, x plus h is getting closer and closer to x. The distance between them is getting very much smaller. Of f of x plus h minus f of x all over h. And that is how we define the derivative. So the derivative of a function at x, where x can be any of the values on the function, is equal to the limit as h goes to 0 of this expression, which is often called the difference quotient. Limit as h goes to 0 of f of x plus h minus f of x all over h. I should mention there are alternate definitions. Some people like to talk about how the derivative of f at a is the limit as x approaches a. Actually, that's sorry, I have to think 1 second here. F of x minus f of a over x minus a. That is an equivalent but alternate definition. This definition is less nice, not because it's like terrible or anything, just because, well, one, this is usually kind of the definition people start with when you're talking about finding the derivative at a point, where you think of a as like just one specific point. Where if you're talking about the derivative of f at x, where x is a variable, you're kind of talking about the derivative as a function, which is what we eventually move to. Secondly, usually this is much easier to simplify. F of x plus h minus f of x all over h, it is almost always relatively easier to simplify the top so that all the things that we have are things with h's, and then factor out an h and cancel with that h. It is much more challenging. Sorry, I'm not giving anyone the finger. I'm giving myself the finger. Much more challenging to simplify the top here so that you can factor out an x minus a and cancel it with the x minus a in the bottom. So that's why we like this better than this. But you could totally say this is a and this is x and say, oh, I mean, it's kind of terrible notation. So I don't want to get to it. Let's do some examples. So there's a whole kind of slew of different functions that we typically talk about finding the limit definition of the derivative of. And there are some classic examples like, I don't know, polynomials. For example, I could say, ooh, I could maybe start with a function. I could say, I want to use the limit definition of the derivative to find the derivative of f of x equal to x squared minus 6x. And you might already know what the derivative is using the derivative rules, right? There are definitely rules for this. You might already know that the derivative here is 2x minus 6. Yeah, I'm going to say something after this. I'm going to think, do I want to use this example? Yeah, that'll be fine. Okay, so I'm going to do some graphing afterwards and show you some stuff. So if I look at the derivative here, well, again, it's the limit as h goes to 0 of, oh gosh, brain, f of x plus h minus f of x all over h. I don't think you need to write this every time, but I'd like to write it to at least so I know that, oh, the person who's grading my work knows I know what I'm doing. But you can probably skip that step. And then we're going to write the limit as h goes to 0. F of x plus h, you might want to write f of x plus h out before you start throwing things in here. If f of x is x squared minus 6x, f of x plus h is x plus h is x plus h squared minus 6 times x plus h. So that's what we're going to have, this minus that, which might not fit very well here. So x plus h squared minus 6 times x plus h minus f of x, which is x squared minus 6x. And to be careful, it is minus all of it. So it's minus parentheses x squared minus 6x all over h. Okay. I feel like I've said this before, but I should say it again. Our number one goal is to cancel that h out in the denominator, right? Right now we have a 0 over 0 type of limit, which is why we spent time talking about 0 over 0 types of limits. And we don't want that, right? We can't do anything with that until we can cancel out that h. So our primary number one goal, cancel out h. We don't like it. We want it to go away. Our intermediate goal is to make all the not h things in the numerator cancel out. Because then once we've achieved that goal, everything left will have an h. We can factor that h out and cancel it with the h in the denominator. So that's always kind of the two-pronged goal. First, cancel out all the not h things on the top, then cancel out the h in the bottom with all the h's that you have on the top. Well, I should say with an h from each thing you have down. We'll see. Okay, so with the limit as h goes to 0 of x plus h squared multiplies out to x squared plus 2xh plus h squared. Distribute the minus 6. So you get minus 6x minus 6h. Distribute the minus sign. Minus x squared plus 6x. All over h. So now, all the non-h terms should cancel out. X squared and negative x squared. Negative 6x and positive 6x. Everything else, 2xh, h squared, and negative 6h have an h in them. So then, you can either do the thing where you just divide each thing by h, which is not my favorite, or you can factor out an h from each thing. So I factor out an h, here I'm left with a 2x. Factor out an h from h squared, left with an h. Factor out an h from negative 6h, you're left with a negative 6. And then this h you have factored out can cancel with that h in the denominator. And then, after you've canceled out that h in the denominator, you're free to just plug in h equals 0 for the rest of the h's, and you get 2x plus 0 minus 6, which is 2x minus 6. All right, so there's your derivative. Great, big deal. Let's take a look at what this kind of means graphically. I might graph these in Desmos in a second, but I kind of feel like I can maybe say something, maybe actually show you more not on Desmos. So let me, I think it's time for some new pens. Not that I have a new pen, just that I want a new pen. So, oh, you're not too terrible. No, you're kind of terrible. Okay, so my original function was the parabola x squared minus 6x. So draw it in red. So x squared minus 6x, or x times x minus 6, has intercepts at 0 and 6. So that's 6 right there. And it has its vertex at 3, negative 9, I believe, right? If you plug in 3 for x, 3 times 3 minus 6 is negative 9. Yeah. So I'm making that a mark of 3. I do want to try and make this kind of precise. So, okay, here's my parabola. Come on, James, draw a good parabola. Ah, so close. Well, we can fix that. This is why you make the marks after you draw the thing, so that they're right where you want them. Okay, great, there's my parabola. There's the function. And now I'm going to draw the derivative. The derivative is the line 2x minus 6 It's got a y-intercept of -6. It's got an x-intercept of +3. Looks like this. Okay. And here's what I want to kind of say about this. So notice, right, that to the right of 3, that my derivative is positive, right? Everywhere over here, my derivative is positive. Also, and this is going to be important later, but it's also important now, that to the right of 3, the original function, well, from 3 onward, the function is increasing. And that's actually something that is always true. The derivative is positive, the function is increasing, and vice versa. The function is increasing, the derivative is positive, which makes sense because if you think about the derivative being the slope of the tangent line, if the function is increasing, then any tangent line you could draw would have a positive slope. In the same sort of way, to the left of 3, we see that, well, the green function is always below the x-axis. So the green function is negative. So f prime of x is negative. We also see that to the left of 3, the red function, again, if we read from left to right, which we always should be if we're talking about increasing, decreasing, the red function is decreasing from left to right. And then we see at the bottom here, where it bottoms out, we see that right here, f of x has a minimum, and we see that f prime of x is equal to 0. This is actually what I was kind of referring to or alluding to when I was talking about that graphing problem I was doing and saying like later on we'll be able to figure out where that minimum point is. We're going to find minimums later on by figuring out where the derivative is equal to 0, where we have critical points. Okay, let's do some more examples. If they're not graphing stuff, but of the limit definition. So there are specific functions you want me to look at, I'm happy to. Otherwise, I'm just going to try and do some classic functions, limit definition of derivative. Sure. So what about something like, something terrible, like f of x equal to 1 over the square root of x. And I want to find the derivative of this using the limit definition. Now, it might not be on your first test, depending on the class you're in, but eventually I have to imagine you will also have a limit definition of a derivative question on the exam. It's kind of it's not an absolute must, but it's pretty standard. So again, I'm just going to, first I'm going to write f of x plus h, because I know I'm going to have to use it. So that's 1 over the square root of, instead of x plus h. So now to find the derivative, it's going to be the limit as h goes to 0, f of x plus h minus f of x all over h. And then we're just going to throw it all in there. The limit as h goes to 0 of f of x plus h, which is 1 over the square root of x plus h, minus f of x, which is 1 over the square root of x all over h. Well, that looks gnarly, right? How do we put those together? How do we put those together? So in this case, if we're subtracting fractions, we need a common denominator. And the problem with essentially when you're adding or subtracting with the denominator is you can't really accommodate that easily. You just have to kind of say, well, the common denominator is all the denominators multiplied together. So I'm going to multiply. I'm going to do it the computationally easier way. I'm going to multiply this expression by the common denominator of those top fractions, which is the square root of x plus h times the square root of x. But again, as I was saying more near the beginning of class, the only thing I'm actually allowed to multiply by in a limit is 1. Or really in general, right? If you're not trying to change something, you're only allowed to multiply by 1. So if I do it to the top, I have to do it to the bottom. Okay, our goal is to cancel that h out, which means we should not distribute it or multiply it through anything. We just leave it as h times this times this. Our goal is to simplify the numerator, so I should definitely multiply at the top. So the limit as h goes to 0 of, so this quantity times this, the square root of x plus h will cancel. I'm going to be left with 1 times the square root of x. This quantity, so when I multiply by this, the square root of x's cancel, and you get minus the square root of x plus h. All over h times the square root of x plus h times the square root of x. I will mention, if you wanted to, you could multiply these out and say it's like the square root of x plus h times x, or the square root of x squared plus xh. The reason I wouldn't is because we know eventually all the other h's are going to go to 0. So I don't want to do any algebra work I don't need to do if eventually that h is going to go to 0 and it's going to be easier to deal with after that. Square root minus another square root. You know what to do. Multiply by the thing. What's it called?
Conjugate?
Yeah, thank you. This one's a little bit messy. So now, multiply by the, so I'm still writing I'm writing the limit every step until I actually get rid of the h's, right? So if you still have h's, you still need to be writing the limit as h goes to 0. Once you don't have the h's, then you should no longer have them. So I'm probably not enough room. Let's see. So when I multiply the tops together, I get the first thing squared, so x, minus the second thing squared, so x plus h. Now notice I made an error. It's the first thing squared, x, minus the entire second thing squared. Right, that's minus the square root of x plus h squared, which is minus all of x plus h. Over, that's a lot to write in that little space. H times the square root of x plus h times the square root of x times the square root of x plus the square root of x plus h. Again, I will mention, you could probably multiply some stuff on the bottom and make it simpler, but I know eventually I'm going to let h go to 0, so I don't want to do any algebra I don't have to do. And do I have enough room? Maybe. Maybe not. Maybe I have to go over the top. So again, the function we're taking the derivative of is 1 over the square root of x. So let's simplify just a tiny bit. I'm going to get the limit as h goes to 0 of x minus x cancels. So you get x minus h, which is just minus h, over h times all of the rest. Square root of x plus h times square root of x times square root of x plus the square root of x plus h. Okay, normally I might show a couple steps here, but I think I'm going to try and do it quick. So I would cancel out this h with this h, right? This h is multiplied by all of that, so I can cancel it out. You have to be able to factor it out to cancel it. Left with a 1 on top. So I've got minus 1 over, sorry, I should say, I've got the limit as h goes to 0 of minus 1 over the square root of x plus h times the square root of x times the square root of x plus the square root of x plus h. So I would write this as, so I'm actually going to go ahead and plug in 0 for the remaining h's. So I'm going to have minus 1 over the square root of x, square root of x plus 0 is the square root of x, times the square root of x, times square root of x plus the square root of x. Square root of x times the square root of x is x, and the square root of x plus the square root of x is 2 root x. So I end up with, sorry, I'm having to erase the problems I go here. That's kind of crazy. I'm getting negative 1 over x times 2 root x, which I might write as negative 1 over 2 times x to the 1/2, or negative 1 over 2 x to the 3/2, or negative 1/2 x to the minus 3/2. Any one of these ways of writing it's probably fine. But the reason I wrote it that way specifically is because it really demonstrates the fact that the power rule would have worked here. Not that we've learned the power rule necessarily, but it's nice to see that, oh yeah, the power rule that we're going to learn, or maybe already have learned, does work. If you think about your original function being 1 over the square root of x, which is 1 over x to the positive 1/2, which is x to the negative 1/2. We will talk about the power rule more in depth next time. I'm just going to say it right now. The power rule says that if you're taking the derivative of x to a power, you multiply by that power, and then the new power is 1 less. So a faster way of taking the derivative, or one of your derivative rules, would be that, okay, I'm going to multiply by that power, so it's negative 1/2, times x to the new power is 1 less. So that's negative 1/2 minus 1. But that's negative 1/2 times x to the negative 1/2 minus 1 is negative 1/2 minus 2/2, which is negative 3/2, which is exactly what we got over there. So the real point is, no matter what way you do the derivative, you should get to the correct answer. Whether you're doing it the super long way, taking the limit definition, or whether you're using one of the rules we learn later on about the how to do the power rule. Are there questions here?
It looks good. I was just like, one thing I got stuck on usually when I worked on these problems was forgetting to multiply the h denominator by the conjugate, or like whatever. I think in like the first step or something, first or second.
With the common denominator?
Yeah. So like you get it into.
I erased the first half.
Yeah, I was like, where is it? Okay. So basically, yeah, thank you. You just reminded me to multiply the h's, I think. Or the bottom part by the, you know what I mean. Okay.
Yes.
Thanks.
Let's see. I think we've got time for one more. So with these limit definitions, they get to be kind of gross. And the point is, half the point is showing you how terrible it is, so that you're super like, yay, we're appreciative of how much easier it is when we learn the power rule, or the quotient rule, or the product rule, or the chain rules. But so we can try and find the derivative of something like x over x plus 3. And again, this is going to be a little bit messy. So the derivative is defined to be the limit as h goes to 0 of f of x plus h minus f of x all over h, which is the limit as h goes to 0. Okay, f of x plus h is not going to be pretty. It's going to be x plus h over x plus h plus 3. Right, just replacing each x with x plus h, minus x over x plus 3, all over h. Again, our job, our goal, our duty is to cancel out that h. So then, again, a common denominator. And the common denominator is pretty much the grossest thing we could think of here. It's x plus h plus 3 times x plus 3. There is no nicer way to do it. You can't just magically add in an h to the denominator here and call it good. So here we're going to get the limit, h goes to 0, of x plus h over x plus h plus 3 minus x over x plus 3 over h times x plus h plus 3 times x plus 3 over the same thing. When we distribute to here, the x plus h plus 3's will cancel. When we distribute to here, the x plus 3's will cancel. So here's what we're going to get. we're going to get the limit as h goes to 0 of. So this times this, the x plus h plus 3's cancel, and we get an x plus h on top times an x plus 3. Minus, we multiply it here, the x plus 3's cancel, and we get the minus x times x plus h plus 3. All over h times this. Again, you do not want to multiply at the bottom, really ever, until after you've let h go to 0. Still writing a limit because it still have h's. So I'm going to multiply at the top, right? Because again, our sub goal, right, our halfway goal, our intermediate goal is to make sure that we cancel all the not h things in the numerator. And to do that, I really have to be able to multiply the numerator. So multiplying out x plus h times x plus 3, I get x squared plus 3x plus hx plus 3h, right? Yeah. X squared, 3x, hx, 3h. And then it's a minus x times each of these things. So it's minus x squared minus xh minus 3x. Right? It's minus x is this, minus that. All over the same denominator left alone. And now I want all the not h things to cancel. Sometimes some of the things with h's cancel too, that's okay. But specifically, this x squared cancels with that minus x squared. This 3x cancels with this minus 3x. And this hx does cancel with the minus xh, right? It's okay, like it would be okay if that didn't cancel since it has an h in it, but sometimes things that have h's do also cancel out. As long as all the not h things cancel, we're good to go. So here is what we are left with. We are left with the limit as h goes to 0 of, I have a 3h on top, and I have this giant mess on the bottom. H times x plus h plus 3 times x plus 3. I can cancel the h's here. I personally like to write one more step, but I'll skip it for a second when we get to the answer. So I'm going to write one more step in the middle here, but you can just say, well, now the rest of the h's go to 0. So I get 3 over x plus 0 plus 3 times x plus 3, which is 3 over x plus 3 quantity squared. I kind of like to write the step where I have the limit as h goes to 0 of 3 over x plus h plus 3 times x plus 3. And then I'm like, oh yeah, I'm plugging in 0 for h, so I get this, which is this. But yeah, right, we definitely did not want to do any multiplying out in the bottom really at all, because in the end, it just simplified to something that was nice. And you don't want to multiply this out, right? You want to leave it as 3 over x plus 3 squared, not as 3 over x squared plus 6x plus 9.